Okay, as part of this week, we're going to go into chapter 8. I'm skipping the moisture chapters for now. We'll come back to them next week. So, right now, we're going to talk about wind. That's the real component of this. What's wind, anyways? And why are we having to learn about it? Well, we want to know why air moves, where it's going to move. If we can tell where air is going, we can see what maybe kind of weather we're going to have. If our air originated, say, from central Canada, there's going to be one type of weather we could probably expect. It'll be cold, it'll be dry. If our air originated out of the Gulf of Mexico, well, maybe it'll be a little bit warmer, a little more moist. So understanding how the air is moving and why is key to understanding what the weather is going to be. So wind is just the local motion of air relative to the Earth's surface. Yeah, guess what? The Earth moves, so the wind's moving already. Some air would be moving. So it's just a change of that motion with the Earth's surface. So what moves air? Well, we talked about pressure. Pressure being a force. Guess what? Force is what moves the air. A force moves your car. A force moves a baseball bat. A force can move a rock that's thrown. You've seen videos of tornadoes probably where they've thrown roofs off houses. That's wind force. So all of those things are forces. So what forces govern the air motion? Well, we're going to talk about pressure gradient, something called centripetal force, Coriolis effect, friction, gravity. So let's just start talking with pressure gradient. All right. Think about a topographic map. If I have a bunch of contours very close together, I'm pretty steep, right? I'm going to walk across where those contours are. I'm walking up slope. That's pretty doggone steep. It may be almost impossible to climb. Well, the same kind of thinking can be applied to the atmosphere. So, the atmosphere is always going to want to get rid of pressure gradients. It's what it's trying to do. It wants the pressure to be the same everywhere. So, in order to do that, think of it as high pressure being a mound of air. Well, I have a big mound of air there, and I have this lower sinkhole somewhere else. What's the air pressure? What's the air going to want to do? It wants to fill in that hole. It'll take what's from the mountain, push it towards that hole. So air will always move from highest pressure to lowest pressure. So when you look at isobars that you've done enough of now to have a fairly familiar idea with them, if they're close together, there's some force. The air is going to be sliding down from that high pressure towards low pressure. If they're very tight together, it's going to be going a lot faster. So guess what? The wind's going to be faster because the pressure gradient is greater where the pressure lines are closer. Most of the time, those pressure lines are going to be closer near low pressures. There's another force, centripetal force. All right, if you ever spun a ball around like a discus person here, spinning it around, why is that ball not flying out into space as soon as you start that? Why is it going into curved motion? Well, it's going into curved motion because it has centripetal force holding it back. Centripetal force is the force that's keeping that object in a curved motion. So when you're going around a curve in a car, why didn't your car keep wanting to go straight? It wanted because of that centripetal force pulling you back. The stronger that centripetal force, the shorter the curve. So if I get rid of centripetal force, we'll move in a straight line. But I do have centripetal force around high pressure systems, around low pressure systems. And it's an imbalanced force. So that means that the air is not moving in a straight line. Newton's first law of motion says if I start an object moving in one direction, it's just going to keep moving. If I only apply one force, guess what? I'm applying a constantly changing force in centripetal force. So the air is going to be constantly turning. The next force is the confusing one. We live on a rotating Earth. If we didn't, I wouldn't have Coriolis effect. So I want you to think about it. If you look down at the top of a ball, start turning that ball one direction. What's the direction of motion that you see from the top? Now, put that ball above you, do the same turning motion, and look at it. What's the direction of motion that you see the ball moving now? They're opposite. That's very weird to me. But that is the truth. And think about it. In one day, the Earth rotates completely around its axis. Well, we know at the top, at the North Pole and the South Pole, there's nothing really to rotate, is there? However, at the equator, there's a long way to rotate. So that is what generates a Coriolis effect. You can see here, I start at one time. Here's 100 degrees longitude, 40 degrees latitude, right here. If I looked up here, so many hours later, it's not moving, is it? However, look at its relative location to how it moved here. And because of that, it is pushing everything to the right in the northern hemisphere. If I was in the southern hemisphere, because it's the opposite spin, it's pushing everything to the left. So that is the Coriolis effect. Very confusing, I know. But it's something you're going to see. And it's stronger closer to the pole. There's more deflection than near the equator. It is absolutely zero at the equator. So the further north the air is, the more it's going to want to turn to the right. The further south, below the equator the air is, the more it's going to want to turn to the left. Another force is friction. All right, friction occurs at any altitude in the atmosphere. However, most friction, strongest friction, is going to be right by the ground. Think about it. If I'm moving along a nice smooth surface, push a cart, for example, along a nice smooth surface with those nice wheels. What's happening? And it's not hard at all, is it? Relatively speaking, depending on the weight of the cart. I did that last week. I was at the beach. So I'm pushing it along, nice, smooth, flat surface of boards. I got off the boards and I am on a lumpy sand. And I mean lumpy. What happened? That cart got a whole lot harder to push. Why? Because friction increased greatly. Same happens on the Earth. Think about it. If I'm over water, I got a few waves, but really there's not a lot of friction. If I'm over land, well, I might have trees. I might have a little hill here. I got a lot more friction. So friction is going to be more over land than it is over water, and certain parts of land are going to have even more. Now, throughout the atmosphere, there's friction that's going to occur all the way through. Turbulence is one of them. It's eddy motion. In other words, air doesn't move in a nice straight line. It kind of oscillates around. I had turbulence described to me as if you pour in creamer into hot coffee and watch the drop of creamer move when it hits the coffee, and how it moves in all kinds of different directions. That's a great example of turbulence. The same holds with air. That is when you're flying an aircraft or whatever, that is turbulence. So it is motion induced by friction at any altitude in the atmosphere. And some things cause more of it than others. Oh, gravity. Wow, Earth does pull things down, right? Well, it pulls everything down towards the center of the Earth. So, yep, that's gravity. Oh, yeah, there's another part of gravity, and this is key. The Earth rotates, so there is centripetal force also there. So there is actually gravity as two forces: the pull between the molecules and centripetal force holding you down on the Earth's surface. While centripetal force is way, way weaker than gravity, it is a force. Everything gravity does pulls down, doesn't impact anything in the horizontal winds, all downward motion. So these are the forces, and we talked about each one. Now, let's start. I have a little parcel of air. What do I call an air parcel? Air parcels are a grouping of molecules of air. They can be 10 feet across, 100 feet across, a mile across. Think of it as a circle. It's a mile diameter, or I'll say in this case, 500 meters diameter. That circle of air is an air parcel. Now, why isn't that air leaving the Earth? There's pressure gradient force in the vertical, right? Pretty strong pressure gradient. Matter of fact, I lose 1,000 millibars. If I go 3,000 feet up, I have dropped 150 millibars. Not even a mile. That is a very significant pressure gradient. Extreme. But why the heck is that air not flying away from the Earth? Because of gravity. Gravity pulls it back. And that balance, keeping that air parcel right there, not moving, even though the air pressure gradient is very strong, pushing it upwards, gravity is equally strong, pulling it down. That's why we have an atmosphere. It's called hydrostatic equilibrium. It keeps that air parcel right where it is. Now, that air parcel can move, but it must move at a constant velocity. In other words, say an air hits a mountain, the air parcel is going to move up that mountainside. That's a constant velocity it's moving, and it's going to move down the other side. Constant velocity. That's hydrostatic equilibrium. It's a very simplification, but it is a great way to think of vertical motion of air. All right, geostrophic wind. So I'm going to start out with a pressure gradient. I got this pressure gradient. 616 millibars, 612, 608. So the air parcel immediately wants to go from the higher pressure to lower pressure. Pressure gradient force, pH. There's immediately going to be a Coriolis effect. As soon as I start moving the air, that's going to want to tend to turn it to the right. So that air parcel, instead of going straight to low pressure, is going to begin a right turn. Gradually, it comes into balance where the pressure gradient force and the Coriolis effect become equal. Now, notice we have not talked about friction, centripetal force, or any of that. All this is two forces. That is a geostrophic wind. It blows parallel to the isobars. In other words, yes, that air parcel started in the high pressure, but it never makes it to the low pressure. Now, we know we have highs, we know we have lows. We have air motion around them. Now we've added another force. Yes, there's pressure gradient coming from the high out. There's Coriolis effect moving it to the right. And there's centripetal force moving it in a circle. Those three are what balances and keeps the air rotating around the high or around the low. Just the opposite direction around the low. So now we add friction. What does friction do? Friction reduces the wind speed. So in other words, you have initial wind speed of the air parcel moving from high pressure to low pressure. Because friction reduces that wind speed, it reduces the Coriolis. So instead of becoming along a geostrophic path, right along parallel, no, it's going to want to move towards low pressure. and away from high pressure. So the more friction there is, the more the air parcel is going to be intending to move directly towards low or directly away from high. That is why at the surface you find winds blowing inwards toward low pressure and outwards toward high pressure. So if I do something in the wind, the atmosphere is a continuity fluid. It's what happens in one spot impacts it somewhere else. Well, I have air convergence. I have a very fast flow of air slowed down for some reason above. And when it slows, it's converging. The air is going to sink. So it comes down to the ground. What happens at the surface? Well, that air being pushed down, it's going to spread the air out. So you wind up moving at divergence at the bottom. Same happens. I have all of a sudden wind speed picked up in the atmosphere. Now we have divergence. Well, down at the bottom, air is going to want to rise to fill that gap. Doesn't want to keep that area, no air in it. So we wind up with convergence at the surface. Air rising means it's cooling. Air sinking means it's warming. Okay. Air rising will begin to tend to produce storms. Air sinking will tend to bring nice weather. Now, as we move over water, we know there's little friction over water. So let's take Lake Erie. If most of you are from Ohio, I have a wind coming out of Canada across Lake Erie. It's not feeling any friction whatsoever as it's moving across Lake Erie, right? All of a sudden, it's getting close to land. What's it feeling? The friction of land. It's going to begin to slow, right? So as it's slowing, there's convergence happening at the surface. If I have convergence at the surface, that means the air is going to begin to rise. As it rises, it's going to produce clouds. That is the reason you have, one of the big reasons why we have lake effect snows. Now, say the air was coming from the south. What happened? Well, it's picking up speed over Lake Erie, right? As it's moving to north, because there's no friction there, you're actually getting sinking motion right along the immediate coast. And because we get sea breezes and land breezes that alternate, sea breezes tend to be more during the day, or lake breezes, where the air has started to rise anyways from warmer over the land. What happens? Sea breeze or land or lake breeze will tend to cause clouds and showers in the afternoon. The land breeze actually tends to sink at night. We push the air away from the coast. We get nice weather. So now let's look at, I wanted to show you changes in airspeed as you go up. This is Detroit today. Notice the wind's very light at the surface. Friction is playing a big role. Winds are a little bit out of the northwest here, just a little above the surface. Then they increase to 50 knots here out of the west. And right in here, around 200 millibars, we probably have what's the jet. Jet is the fastest winds. So we have fastest winds right around 250 to 200 millibars. The jet stream is higher during the summer because air is pushed apart when it's hotter. The jet stream rises in summer and lowers in winter. Here's the jet stream. Also looking at the surface, notice there's a nice low up here over New England. Lots of southerly winds and crossing isobars in towards the low. Oh yeah, high pressure, they're pushing across isobars the other way, towards low, but away from high. Finally, here's a 300 millibar chart. Here is geostrophic flow. Look how it contours, follow the contours. So all of this, everything you just learned, is ways of looking at how air is moving. So let me know if you have any questions about this.